Morning.
Hi, so welcome to part 2 of the land use and land cover mapping tutorial using Python and Google Earth Engine. So in this second part of the tutorial, you'll learn how to download your own Sentinel-2 satellite images using Google Earth Engine. And you'll also learn how to use a trained model from the previous tutorial to automatically generate a land use and land cover map for a region of interest. So let's get started. So we'll start with an introduction to geospatial data. Um, so our goal here essentially is to introduce basic concepts and commonly used tools to manipulate, analyze, and visualize geospatial data. So our target audience are those who are new to Python as a tool for geospatial data analysis, as well as beginners in geospatial data analysis who are looking for tools to get started. So I'll start with a description of common spatial data types. Spatial data observations essentially focus on location, and there are two main types of spatial data. We have vector data, which are basically points, lines, and polygons. Each vector object can consist of one or more XY coordinate location. Vectors can be used to represent, for example, locations of places such as schools or hospitals, roads, or country boundaries. Now, these vector objects can be stored using spatial data formats such as GeoJSON, GeoPackage, or shapefiles. The second type of spatial data type is the raster data, which are composed of a grid of pixels. So examples include satellite images, nighttime light maps, and digital elevation maps. In these maps, each pixel represents a value or a class. So for example, the red, green, and blue values in satellite images, the nighttime light intensity in nighttime light maps, and height in elevation maps. So raster data are commonly used as commonly stored as geotiffs. And you see here graphical representation of rasters, which again are a grid of pixels, versus vectors, which are basically points, lines, and polygons, and how they can be used to represent the real world. Next, I'll be discussing very briefly coordinate reference systems, or CRS. So essentially, map projections are 2D representations of the Earth on a flat surface. But because the Earth is spheroidal, there is no single most accurate way to represent the Earth in these two dimensions. And this results in a number of coordinate reference systems that serve different purposes. So I do highly recommend you watch the Vox video on why all world maps are wrong. So these coordinate reference systems provide a method for defining real-world locations in geographic space. These systems determine not just the coordinate locations of objects, but also how your map looks and how distance is calculated. Now, geospatial data, whether vector or raster, is always accompanied by CRS information. So two common CRS systems, or sorry, coordinate reference systems are EPSG 3857 and EPSG 4326. So in this tutorial, we'll be using this latter CRS. Now, in terms of the geospatial data processing tools, we'll be using mainly Google Earth Engine, which is a public data archive of petabytes of historical satellite images and geospatial datasets. So in this tutorial, we will use the Python Earth Engine API to access the Sentinel-2 RGB images. I would like to note that you will need to sign up for access to Google Earth Engine using this link. I'll also be showing you how to use GeoPandas, which essentially extends the functionalities of pandas to add support for geographic data and geospatial analysis. Raster.io allows us to work with raster data, such as satellite images, which again are often stored in GeoTIFF format. So Raster.io allows you to read and write these formats and perform advanced geospatial operations on these data sets. And lastly, Folium allows you to visualize geospatial data on an interactive leaflet map. So for more information, do check out this comprehensive list of Python packages. So we'll start by installing all of the relevant packages, which I've already run here. So this can take a couple of minutes to run. And then once this is finished running, we can now import the relevant packages for geospatial data processing, visualization, and also the deep learning libraries, which we will be using to load the previously trained model from our previous tutorial. Also, do mount your drive so that you can use Google Colab to load and save data into your Google Drive. Here we authenticate Google Earth Engine, so make sure you've signed up for access to Google Earth Engine, and once your request has been approved, which can take several days or so, you should be able to access the Google Earth Engine as such. So you will need to specify the project. So here I just use the default project that I have on hand. All right, so next we can proceed to downloading the country boundaries. So to download the administrative boundaries of our country of interest, we will be using boundaries by the William and Mary GeoLab, which is basically this website here, an open database of political administrative boundaries. So it provides a free and openly accessible global database of administrative boundaries for every country in the world. And we use the API to access these boundaries using the simple query here, where we specify basically the ISO and the administrative boundary level. So we have different administrative boundaries depending on the level. So these represent essentially each level of administrative hierarchy. So in this example, we choose Germany as our area of interest. So we set our ISO code to the EU and our administrative level to level 2. So let's go ahead and run this. And this should return all the level 2 administrative boundaries. Oh, sorry, this is level 3. Oh, sorry, I should update this, but this is level 3 administrative boundaries in Germany. So you'll find this here. And specifically, we'll be focusing on a specific administrative region called Borken, which if you plot it here, shows you this region here. All right, so next we generate our Sentinel-2 satellite images. So I have already somewhat discussed in the previous tutorial how the Sentinel-2 satellite images can contain more than 3 bands or channels. So in this tutorial, we used only the red, green, and blue bands for land use and land cover classification. However, Sentinel-2 multispectral data does contain rich information that can be useful for a number of different applications, including crop yield estimation, vegetation health monitoring, informal settlement detection, etc. So I do highly encourage you to explore the full potential of Sentinel-2 imagery for climate-related applications. So here, we define a cell or a function. We define in this cell a function to generate the Sentinel-2 image from Google Earth Engine using Python Earth Engine API. in order to minimize cloud cover, we aggregate a collection of images over a period of time as opposed to obtaining a single image on a given date. So we create this function called generate image, where we specify the region, we specify the product, which is indicates Sentinel-2 from Copernicus. Here we choose the dates to be, well, the default dates are 2018 to 2020. And the cloud percentage here is set to 10%. So as I mentioned, we get the median aggregate of all of the images between the specified dates, and only look at the RGB bands, essentially clipped to or limited to the region of interest. So let's go ahead and run this. And if we run this cell here, it should generate the Sentinel-2 image for a region of interest in Germany called Borken. So this here gets all of the images between 2020 within 2021 and gets the median aggregate of these images to produce this somewhat cloudless composite Sentinel-2 satellite image here. All right, so these next few lines of code show you how to export the Sentinel-2 images into the local Google Drive. So this can take some time. So for example, you can choose export Borken.tiff, and then you can run task status, which should tell you what the status of the task is. So it should start from ready to running. So now it's running to complete. So you can check the status of the task using this link here. So you should see here that Borken is currently running. So I'll go ahead and load a previously downloaded image of Borken. So you see here. So once this has completed, it should download to your local Google Drive, and you should be able to visualize the image as follows. So let's give it a minute. All right, there you go. So you see here the outline of the geoboundary along with the downloaded image. So next, we want to generate 64 by 64 GeoJSON tiles across this image. So remember that in the previous tutorial, we trained a deep learning model on the Eurosat RGB dataset, which consists of 64 by 64 pixel Sentinel-2 image patches. So this means that we'll need to also break down our huge Sentinel-2 satellite image into smaller 64 by 64 pixel tiles. So let's start by creating a function that generates this grid of 64 by 64 square polygons. So here we use the raster.io Windows window utility, which is given here, where we specify the size to be 64. Let's go ahead and run this. And once you run this, it should return a list of tiles of size 64 by 64 pixels across the image. So if you visualize it, it should look something like this. So let's wait a moment. Right, there we go. Now, if you notice that, a lot of these tiles fall within these uh within they fall outside of the boundaries, um which are basically the black or empty regions. So using our model to predict on these blank regions would be computationally wasteful. So instead, we can get the intersection between the boundary, the polygon, the region boundary, and the 64 by 64 grid tiles. And to do that, we use the GeoPandas S-join function. Um, with the following predicate within. So we want to get only the 64 by 64 tiles that lie within the geo boundary of Borken. So let's go ahead and run this. And there we have it. So now we have the 64 by 64 tiles that are within the geo boundary of Borken. All right, so let's visualize a single cropped image. So basically what we do here is we take the polygon, we crop the raster image of Borken so that we only get the 64 by 64 image of that specific tile, as you can see here. And from there, we can get each of these images and run it through the model to generate our prediction. So here we load our best model that we trained from our previous tutorial. So also recall in the previous tutorial that we applied a set of data transformations to our test set. So before we run our new images through the model, we'll also need to apply the same transformation to our new data as well. So let's go ahead and run this. And this function here basically crops the source image using the 64 by 64 tile geometry, and then iterates through each 64 by 64 tile, gets the cropped image, and generates a prediction for each of the cropped images using the trained model. So we can go ahead and run this. So here I won't necessarily run this during the tutorial because it can take quite some time, up to almost 15 minutes. But the result should be basically for each tile, you'll have corresponding prediction given by this prediction column here. All right, so let's finally visualize the interactive land use land cover map using Folium. So I'll go ahead and download a previously generated prediction dataset. And then we map each label to a corresponding color, just so it's a little more meaningful when we visualize it on the map. And then finally, let's visualize the predictions on a Folium map. So let's give this a minute. And there we go. So you can see here the ML predictions, where, for example, the pink areas indicate areas in the residential area. So, grid tiles in residential area. So you can unclick this and you should see that these are mainly residential. The red tiles are in industrial. So if you unclick this, or sorry, if you toggle this on and off, you should be able to find that these red tiles do generally tend to look like industrial areas. Now we do have some, I would imagine some of these are also model errors. Like for example, here it predicts a river, despite not having a river here, I believe. So this can be improved by further training your model or doing hyperparameter tuning, and finding ways to further to create better models. So that basically ends the tutorial. So just to recap, you learned how to download the Sentinel-2 satellite image for a region of interest in Germany using Google Earth Engine, and you applied a trained CNN model to generate a land use and land cover map. So as an exercise, do try training your own model and applying it in a new country and see how well does the model perform in new geographies. Some limitations, you'll find if you have tried applying the model to another region in the world, you'll find that the model might not always perform as well for certain areas. So we do know some of the limitations here. So one is limited scene categories. The 10 land cover classes in Eurosat dataset are obviously not representative of the complex content of remote sensing data. These class labels are not mutually disjoint, so an image can, for example, contain both a highway and a residential area, and their union doesn't cover real-world distributions of land cover classes. So certain land cover types like desert land or aquaculture are not represented in the dataset. There's also limited model transferability. So the dataset, the Eurosat dataset, of course, consists of satellite images distributed across Europe, which suffers from limited geographic coverage, restricting the model's generalizability to other regions of the world. So I do recommend collaborating and stronger data sharing efforts to improve global coverage of annotated remote sensing datasets. All right, so I've listed here some other remote sensing datasets that you can try out and explore. If you're interested in learning more, do check out the Climate Change AI paper on tackling climate change using machine learning. Check out our wiki tutorials in our website, and do attend our events, workshops, and consider signing up for our newsletters. So thank you so much for your attention, and I'll see you in a future tutorial.